Thanks, Randy. Again, for those of you who don't know, my name's Derek Nearplant with Federal Highway. And again, I'll be moderating this afternoon's session. We'll be going through case studies, state and contractor experiences, putting together a balanced mix design. Just a couple comments before we start. This is really unique meeting and conference here today where we're really focused on the implementation. Balanced mix design has been talked about at a lot of levels, but often it's the research. It's the purely technical items really that we're looking to focus. And I think we have some speakers in discussion today to take that and put that into practice. How do you put it into practice? And that's what the focus of this is, really unique, and appreciate the opportunity to be part of it. As far as Federal Highway, we're excited to support agencies on their road to implementing balanced mix design. We've been collaborating with NCAT on some of this information as well. Randy mentioned our workshop that we're certainly offering out to agencies and states to aid them in seeing the road ahead to get to balanced mix design implementation. So certainly feel free to catch me at any time over the next day, and I can certainly talk to you about it. For this afternoon's session, we're going to go through states Vermont, Virginia, and New Jersey. What we will do is we'll have each the state DOT and the contractor experience and present. We will hold questions. We do have a question and answer session all at once that we'll be doing. So for those of you in person, we'd ask just kind of maybe write your question down or hold it. And for those of you online, you can type it into the chat, but we won't get to it until we do the full question and answer session later. Right. So with that, we'll kick it right off and get into our first state, which will be the state of Vermont. And our first speaker will be Aaron Schwartz. Known Aaron for a couple of years, and Aaron is the bituminous concrete engineer for the Vermont Agency of Transportation, where he has 6 years of experience, 5 of which at V-Trans. So everyone welcome Aaron.
Thank you, Derek. So good afternoon, everyone. My name is Aaron Schwartz. I'm the bituminous concrete engineer for the Vermont Agency of Transportation. And today I will be discussing the agency's perspective regarding the balanced mix design for what we've been doing. So first off, I want to thank our field and lab technicians at V-Trans for providing the for obtaining the split samples at the lab, and then having our lab technicians fabricate the specimens, reheating them to the compaction temperature, and fabricating the specimens, splitting and for the Hamburg and the iFit. And then I would also like to thank the Vermont QC team with Pike Industries, as well as the central lab team at Pike Industries, as they were the contractor / producer for the 3 pilot projects that we did. And lastly, I would like to thank the National Center for Asphalt Technology for giving me the opportunity to speak today, and also especially Dr. Randy West for asking me to present. So first, I'm going to talk about the motivations for why we decided to go with balanced mix design, as well as the tests that we did, the initial benchmarking that we did, our selected BMD approach, the pilot specification itself. I will briefly go over the 2019 projects that we did along with the 2020 projects, discuss some of the impediments and constraints that we found during using our tests in QA production. And then I will conclude I will summarize everything and then conclude with what we're doing moving forward. So the question is, why did we decide to move ahead with balanced mix design or start pursuing balanced mix design? So since 2008, under state law, we are required to consider or allow up to 50% wrap by weight in our asphalt mixes. And since 2018, we have allowed up to 3% RAS by weight in our mixes as well. It's worth noting, as I will indicate later in this presentation, that most mixes have no more than 20% wrap in general because we have grade bumping requirements in our PG binder specification. In addition, we were also seeing various distresses in our asphalt pavements, mainly raveling and rutting on our limited access highway system, as in our interstates, basically. We were also seeing all three cases of cracking, as in fatigue cracking, thermal cracking, and reflective cracking. And this is because of what I like to say, we are an unintentional composite pavement state on our regular roadways because there are concrete slabs dating back from the 1930s and 1940s that were placed below the asphalt pavement layers. And as most of you can attest to in the room, what we found with the original performance tests developed with the super pave mix design methodology was that they were too complex and the equipment was too expensive. So in Vermont, we only implemented the volumetric aspects of super pave. And lastly, and most importantly, we wanted to increase the amount of collaboration that we have with the asphalt producers and amongst ourselves, because we share a common cause, ensuring that the right materials are being used at the right cost and at the right time. So now I'll talk about the balance mix design tests that we chose. So in 2015, we purchased the Hamburg wheel tracker, and we chose that test to evaluate rutting and moisture susceptibility, primarily because it is a torture test in principle on HMA mixtures. And we suspected that raveling was moisture susceptibility related. And in addition, we also shared a mutual dislike with the asphalt paving industry in Vermont regarding the TSR test parameter that's performed in accordance with HWTT 283. We thought as though it did not reflect the actual moisture susceptibility and stripping issues that we were seeing in Vermont. And then for the cracking side of balance mix design, we chose the Illinois Flexibility Index because it was identified as a candidate test for thermal and fatigue cracking in NCHRP project 9-57. And at the time we made this decision in 2017 is that we were anticipating an increase in our recycled asphalt materials content, particularly RAS, which we did implement in 2018, as I noted before. We did look at the other two SCB tests, Louisiana and the Minnesota test, but we either found them to be not used outside the southeastern US in the case of Louisiana SCB, and we considered the Minnesota SCB tests to be too expensive for what we needed because we needed to purchase an environmental chamber. So next I'll talk about the benchmarking, and upfront I will say that benchmarking has been the most challenging aspect of incorporating balance mix design in Vermont. So we began sampling plant-produced mixtures in 2015, soon after we purchased our equipment. And essentially, we reheated specimens up to compaction temperature. Initial specimens were gyrated to 60 millimeters per T324, the AASHTO procedure, but since last year, we've been gyrating to 62 millimeters per feedback in our paving association meetings. We initially did testing at various temperatures ranging from 40 degrees Celsius to 55 degrees Celsius. But then in 2016, FHWA suggested that we test all specimens at 45 degrees C due to the climatic conditions in Vermont and to align with procedures in our neighboring states, Maine and Massachusetts. And after we presented our initial data in the winter 2017 meetings with our paving association, the producers began split sampling plant-produced mixtures and following the same fabrication procedures that we were, assuming they had Hamburg equipment in their labs, and almost half of the producers as of this year now have Hamburg equipment in their possession. Also in 2017, there was an executive level decision made to mandate the use of polymer modified binders for all agency paving projects moving forward. And because of concerns in our paving association meetings regarding the massacre test at the time and tank storage requirements, we decided that the simplest path forward was just to specify PG 7028 binder as a baseline. So Allow me to go over the 2015 and 2017 data very briefly. Most of the data from 2015 and 2017 consisted of varying PG binder rates, as indicated on my slide. All the data from 2015 wasn't entirely tested at 45 degrees Celsius. And for that reason, and along with the fact that most of the softer binder mixes tended to fail at 12.5 millimeters before reaching 20,000 passes, in addition to our programmatic switch to PG 7028 binders, we ended up not using that data in constructing our pilot specification. So now I'll talk about the 2018 data. As you can see, the average and standard deviation rut depth for mixes with PG 7028 binder was 4.1 millimeters and 2.22 millimeters. For PG 5828 binders, it was very close to hitting 12.5 millimeters rut depth as an average. Not shown on this slide is the average rut depth and standard deviation for our 9.5 millimeter mixes, which we use as our wearing course. And that is 6.85 millimeters and 4.15 millimeters as a standard deviation. And I will get into detail about that a little later. It's also worth noting that most mixes with 7028 binder did not strip based on visual analysis of the final plot, where the strip slope was less than the creep slope, or began stripping after 15,000 passes. So for our initial benchmarking of the iFit, we began sampling plant-produced mixes in 2018. All procedures in the AASHTO method were followed, with the one exception being that we were gyrating specimens directly to 50 millimeters instead of fabricating 160 millimeter specimens and then cutting 50 millimeter slices out. And that was because we were on the fence about whether we wanted to purchase a tile saw or not. We eventually did during the middle of the construction season, but in our first attempt at following the proper procedure, one slice of the 160 millimeter specimen ended up being 52 millimeters thick on one side and then 48 millimeters thick on the other. So that was an oversight on our part, and we realized that we needed to purchase an additional jig, which we did. And after some trial and error in winter 2019, we have been following the proper AASHTO procedure ever since, starting in the 2019 season. And likewise, the producers began split sampling of plant-produced mix for iFit and following the same procedures. We were assuming they had the equipment, and as of a few weeks ago, half of the producers in Vermont now have iFit test equipment. So the 2018 data for the iFit, like I noted before, was entirely consisting of specimens that were fabricated directly to 50 millimeters. And it's also worth noting that the majority of results from 2018 consisted of mixes with 20% wrap, and there were no virgin mixes used whatsoever. It's also worth noting that as you'll see with the type 2, which is our 19 millimeter mix, as you'll see in the table, the average flexibility index was 13.5 and the standard deviation was 4.77. And that we thought was alarming, and we realized that was because most of the material came from one specific plant for one specific project. And it was also worth noting that we did not see any major differences between mixes with PG 5828 and PG 7028 binder. So based on this initial benchmarking, what we concluded was that we didn't have enough reliable data for our 19 millimeter or 12.5 millimeter mixes to include them in our pilot specification. So we ended up using only our type 4S 9.5 millimeter mixes if they were being used as a wearing course in our specification. And we were comfortable with the numbers we were getting out of the Hamburg, but we wanted to we wanted the mixes, or we wanted the FI criteria to be strict, if you will, such that the mixes were a little bit more soft in general. So we did that. So in order to develop our criteria, we just used the average and standard deviation and raised or lowered the bar accordingly based on which test was being done. We also realized in our discussions in our Winter Paving Association meetings that plant mix lab compacted specimens are not the same as lab mix lab compacted specimens, and that we needed data to represent conditions at every point in the mix design, during the mix design stage, if you will, meaning specimens for balanced mix design needed to also be tested in the same way that mix designs are generated. So we issued an addendum, which in Vermont we call a general special provision for all projects beginning in 2020, requiring that Hamburg and IFIT results be provided for informational purposes only, such that we can capture mixes that we were not split sampling or anything of that nature. And like I noted before, benchmarking has ended up being the most time-consuming aspect overall, and we're still doing it to this day. So now I'll talk about the mix design procedure in Vermont. In Vermont, it's largely a paper check overall, but we do improve the constituent ingredients like the PG binder and the aggregate sources on an annual basis per our quality assurance program. We used to require mixed design specimens to be provided or shipped over to the lab for approval, but we found that to be redundant at some point. We generally look at air voids and VMA and ensuring that the gradation and aggregate consensus properties are compliant with our specifications and the AASHTO standards. We have not been able to distinguish a direct link between designing to 4% air voids and our observed pavement stresses. So we haven't seen a reason to adjust our 4% air voids target for mixed design approval as part of this balanced mix design. And for these reasons, we've chosen approach A as part of our specification, which is volumetric design with performance verification. So now I'll get into the details regarding our special provision. So we developed the same criteria for both mixed design and during mixed production. And we realized in hindsight that was not the best idea. So for the Hamburg, we specified a maximum rut depth of 10 millimeters overall and a stripping inflection point minimum of 15,000 passes. And then for the IFIT, we specified a FI of 10.0 minimum. We also eliminated TSR testing completely, and this was largely based on findings in New England Transportation Consortium Project 15-3, which validated our concerns that the TSR test parameter was not reflective of moisture susceptibility and stripping in Vermont. So for our pilot spec, we decided to do a percent within limits approach for QA. So we set an arbitrary rejectable quality limit, or RQL, of 60% for the rut depth, SIP, and FI during mixed production. And if the PWL fell below 60% during production, corrective action would need to be done by the contractor to bring the mix back into compliance. And if corrective action was unsuccessful, then the mix design that was used would be rescinded. So I'm not going to spend too much time on these two pilot projects that we did because, as you can see, the quantities were rather small, being under 10,000 tons. The key difference between these two projects was that one project had a design gyration specified as 50, and then the other had a design gyration specified as 65 gyrations. And one important thing to note is that in Vermont, our QA specifications define an air voids lot as 3,000 tons. So we decided to align the sampling frequency for performance testing such that there would be one set of performance test results for each air voids lot, in essence, creating the performance test sublot. However, on the second project noted below, I made a mistake in determining the final tonnage that was going to be used on that project. So the contract was amended via a written order by the resident engineer of that particular project to change the sampling frequency and testing frequency for our BMD spec to 2,000 tons per lot in order to yield 3 sublots to calculate a PWL. So for the mix design on the first project, the RUT-DEF and SIP were fairly well. It's worth noting that the SIP for this particular project was basically spit out from the machine directly, the contractor's Hamburg machine directly. And the flexibility index was 17.2. As you can see with the results during production, the mix was generally softer overall. The PWL of 67 for the stripping inflection point was likely due to the fact that the very first sublot was ended up stripping below 15,000 passes. And we cannot explain why that occurred, given that the mix design did not strip whatsoever. So for the second project, interestingly enough, the average RUT-DEF was 6.5 millimeters, which we found interesting considering that this project specified 65 gyrations, whereas the first project specified 50. And the FI was extremely high, but then as you can see during production, the FI became something more realistic, if you will. And again, the stripping inflection point PWL during production was 57, which was below the RQL. But by the time we calculated that PWL, we were not able to enforce the corrective action mechanism in our spec because production had ended on that particular project. So from 2019 and 2020, we took another look at the special provision, made some minor adjustments to the language to address some issues that we found. And we also identified a larger project for the 2020 construction season. This new project that we chose ended up being close to 27,000 tons overall, which yielded 9 sublots of performance test results. And design was 65 gyration, and like the first 2 projects, producer Pike Industries chose to utilize 20% wrap. So during the mix design results overall were fairly good. They met the specification overall. And then during production, everything had a PWL of 100, but as Cheng will note in his presentation, there were some concerns that we do need to address further down the road. So there are some impediments and constraints to using the Hamburg and the iFit in mixed production overall. For us, one of the issues was data retention. For the project in 2020, there was a network outage issue that caused the first sublot of Hamburg results to not save in real time as the test was being ran. So because of that, we basically tossed out the first sublot from the PWL calculations overall, because that would have messed everything up, and we only treated the results for the first sublot as investigative only. In addition, we sometimes see noise in our Hamburg test equipment in one of the wheel path measurements, and we've attributed that to an electrical issue in one of the wheel path LVDTs. And this has been a recurring issue for us since the 2017 season. And basically, the data from the 2017 season was not necessarily used in any data analysis because we found the data to be unreliable when the noise was most prevalent. Another issue that we found was that turnaround time in mixed production is also an issue. So in Vermont, under our math density spec, which involves testing roadway cores, acceptance testing must be turned around, or excuse me, let me start over. Roadway cores for math density acceptance must be turned around no more than 10 days after the specimens arrive at our lab. For the pilot projects in which we piloted balanced mix design, performance test results were turned around within a month after the materials were sampled at the plant. But typically, whenever we split sample, it usually doesn't happen until at least a month after the specimens are sampled and arrive at the lab. And sometimes the testing will not occur until after the construction season is over. And in Vermont, the winters can get very cold, so there's a lot of downtime. The first few months of the COVID pandemic kind of exacerbated these issues, and there was a delay in processing the results from the 2019 season. And lastly, another issue that we found was that we were starting to ask ourselves, is 3,000 tons too frequent or is it just enough? What we realized is that you have to right size the sampling frequency for what type of paving project is being done, where the project is located, how much risk there is regarding other materials besides HMA, what level of oversight needs to happen by agency inspectors, everything of that nature. And for these reasons, we don't believe that the Hamburg and the iFit are appropriate for use in mixed production anymore as part of a Q8 specification. But we're comfortable enough to implement everything as part of a go, no-go specification for mixed design approval. And lastly, we find that aging in the relationship to field performance is important. In New England Transportation Consortium Project 18-2, our Hamburg and iFit data was paired with data from the agency's pavement management system to draw a correlation. And unfortunately, I will concede that we have not conducted a site visit on any of the pilot projects or windshield surveys for that matter, to see how the pilot specification pavements are holding up, primarily due to COVID, but we have every intention of doing so in the near future. So in conclusion, the special provision that we piloted is unofficially on hold. We're not using it this time until we focus on other specification changes that we're making, including a tiered quality assurance approach for HMA, and that everything for mixture testing will have a pay factor tied to it. And we will also be incorporating the delta TC parameter for our PG binder specifications, and also move ahead with specifying the Massacre PG binder grading system under AASHTO M332. Right now, we're doing AASHTO M320, as you can probably guess. So for performance testing, we are looking at the ideal CT as a surrogate test during mixed production, or even as a replacement to the iFit for mixed design approval. And we're going to start looking at the ideal RT as a surrogate test for the Hamburg during production as well. We've also began testing roadway cores in the Hamburg, and the reason why we're doing this is because, well, what better way to determine rutting and moisture susceptibility than by using samples representing in situ conditions after placement. We're continuing to benchmark all mixed designs, as I noted earlier, as part of designing a go, no-go specification for mixed design approval. And in addition, we are in preliminary discussions with the producers and third-party labs, and possibly with other state DOTs in the New England region to conduct a future round-robin study on performance tests. And lastly, we are asking the following questions, as in, what are the effects from aging on performance tests and mixture performance overall? What happens if we age the specimens and or volumetrics are changed? What happens if we design to 3% air voids, or if we design to 5% air voids, like what's happening in Indiana? Or what would happen if we decided to open up more sieves in our super paved specifications? And we also believe that an increase in recycled asphalt materials content is important. And a lot of these considerations we think will be answered by looking at aging procedures in the future. So again, I want to thank everyone for giving me the opportunity to speak today, and I will hand it off to my colleague Derek to introduce our next speaker.
All right, excellent. Thanks, Aaron, for kicking us off. Now to kind of complete the Vermont story here, we'll get the contractor's perspective from Cheng Ling, who is the technical manager with Pike Industries, which is a CRH company. He has his PhD from the University of Wisconsin and 4 years of experience with CRH companies and Pike Industries. So come on up and we'll get your presentation started.
All right. Good afternoon, everyone. And also to those who are sitting in front of the computer and watching our sessions. I hope everyone is staying safe and healthy. And it is my pleasure today to stand here and talk about our experience from the contractor's perspective during the balanced mix design implementation in the state of Vermont. First of all, I would like to acknowledge Vermont Agency of Transportation for sharing their data as part of this presentation, and also their willingness to work with the paving industry during the specification development. I would also like to thank Pike Vermont Quality Control Team and the Central Lab team for their hard work during the sample preparation and testing. I'll first try to give a brief introduction about the BMD implementation status in Vermont and also Pike's effort during this process, and talk about some of our recent experience through a pilot project and the lessons that we learned from this pilot study. Other than that, I'll try to share some of our additional thoughts as regards to the potential mix adjustment in order to improve the balanced mix design test results, and also the next steps for us moving forward. I think Aaron has already talked a lot about the BMD implementation during his presentation, so I will just go over this slide quickly as a refresher. So VTrans has adopted BMD Approach A, which is volumetric design with performance verification in their specification development. They issued the special provisions in 2019 and have constructed 3 pilot projects so far. In the special provisions, the spec limits were applied to type 4 9.5 millimeter mix only. And in the Hamburg, a maximum rod depth of 10 millimeter and a minimum stripping inflection point of 15,000 passes were required. And on the IFIT side, a minimum of 10 for the flexibility index was required on both short-term urban age lab mix and also the radial production mix. Other than that, a minimum quality level of 60% was also required during the PWL calculation through the production. Also note, starting from early 2020, both Hamburg and IFIT results are required in the mixed design submittal for other state projects, but just for information only. Also, as Aaron just mentioned, that the special provisions has been put on hold until further data collection is complete. Regarding the balanced mixed design effort at Pike, we first purchased the Hamburg machine for Vermont QC in 2017 and bought the IFIT jig along with the saws associated with this test in 2019. At that time, we also bought another set of test jig for ideal CT test, which turns out to be one of the very popular cracking tests across the country today. And earlier this year, we bought another set of hydraulic machine which can run both IFIT and ideal CT and set it up in one of our Vermont quality control labs. We have our senior QC technicians trained and run these performance tests. And running those tests are pretty simple and straightforward, and a minimum training is needed. However, interpreting the data and understanding the data took a little longer. Specifically for the IFIT data out of the test jig and the tablet, since that needs some extra data manipulation through the Illinois IFIT program. So that part took us a little longer before getting used to that. Also, we've been working very proactively with VTrans on the split sample testing, the data sharing, and also had a lot of great discussions on the specification development over the winter meetings. I'll talk about our recent experience from a pilot project that we constructed for VTrans in 2020 season. The project is Windsor Heartland Resurfacing Project as part of US 5 with a total length of 13.7 miles. It was constructed in summer 2020 with a total tonnage a little bit over 26,000 tons. The job was divided into 9 lots with 3,000 tons per lot. And the mix used was a type 4 9.5 millimeter 65 gyration mix with polymer modified PG70-28 binder. The performance test results in mix design showed that the mix had an average had a Hamburg rod depth of 1.77 millimeter, very decent, and an FI of 11.8 using binder source B at the design. However, later in the production, we switched the binder source to another source, A, across the whole production. And later during the off season, we gathered the raw materials and ran the lab verification on the same design using binder source A. And we found that the mix with binder source A actually gave a much lower flex wind index compared to the binder source B. At that time, we also checked the CT index of the mix, which turned out to be 57.6. Here's a quick overview of the production acceptance test result from VTrans. Overall, on the Hamburg side, the mix had an average rod depth of 3.6 millimeter, and no stripping inflection point was identified. And on the IFIT side, the mix had an average of 15.4. And the quality levels calculated in the PWL specification were 100% for all the mixes across the production. During the production, we worked very closely with VTrans on split sampling the mixes across all 9 lots, and also work with them about the results comparison. VTrans completed their test first, and we strictly followed their practice, including the sample reheating and sample fabrication to minimize the variability on the sample preparation process. And here are the comparison of the Hamburg rod depth between us and the agency numbers. VTrans numbers are represented by the blue bars, and our numbers are represented by the orange bars. As you can see, our numbers line up very well with agency's numbers. And VTrans got an average of 3.62, and we got an average of 3.51, very close. And the variation of the mix across all 9 lots through the production represented by the standard deviation in this table for VTrans and us were also close, with VTrans getting a 0.69 and we got a 0.72. Let's take a look at the IFIT comparison. So the majority of the data from either VTrans or us actually passed the spec limit of 10, except for a couple borderline values from us. And VTrans got an average of 15.5, and we got an average of 12.5, which seems to be lower than VTrans. And later, the further statistical analysis also showed that there was a significant difference between VTrans number and our numbers. which probably can be directly seen from the figure that V-trans got a consistently higher number than us. Other than that, the variation across the production represented by the standard deviation for both us and V-trans numbers still close, around 2. And the repeatability of the test, this test conducted by V-trans and us look pretty good overall with an average coefficient of variation of 18%. Some of you probably have noticed that there's a significant difference between the production numbers and the design numbers. Here's a quick overview and direct comparison of the performance test results between the production mix and the design mix. So you can see from the table that on the rotting side, the rot depth out of the production mix gave a much higher value compared to the design mix, almost double. And on the cracking test side, both cracking tests, the IFIT and the ideal CT, on the production mix actually yielded a much higher number compared to the design number as well. It seems that the production, at least out of this pilot study, tends to be softer than the design mix. And in order to further verify this trend, we dig into the database, the mixed performance test database shared by V-trans, and identified all the mixes that shared the same mix design as the pilot project that we produced in 2019 and 2020 season. And here's what we found out of the IFIT numbers. The design number is represented by the red horizontal line, which is 5.5 if you recall. And all 13 mixes that we were able to find all have values higher than, out of production, all have values higher than 5.5, which was a design number. In fact, there are many factors in the production actually that can affect the mixed performance test result, such as the aging condition, which includes the silo, which is related to the silo condition and also the silo storage time. The production variation, specifically on the AC content and 200s, the switchover of the asphalt binder source, the aggregate property change, and even the wrap source change. And all these factors can affect the BMD test results. I want to specifically talk a little more about the impact of asphalt binder source, as switching the binder source is pretty common among the paving contractors, depending on the availability and the cost of the materials. However, unlike the super volumetric design, the balance mix design test result could be very different if a different binder source is used. So in this figure, location number 2 is where the mix for the pilot project were produced. At that location, the nice aggregates are primarily used. As you recall that the binder source A, which was used in the design verification, yielded a much lower FI value compared to the binder source B. Something even more interesting that we found later is when we took the same binders from these two sources and ran another verification at a different location where the limestone aggregates were primarily used, we noticed the ranking was completely reversed. And this time, the binder source A actually gave a higher FI values than source B. So this tells us that there may not be a consistent trend when evaluating the impact of asphalt binder source across different locations. As aggregate source could also matter, caused by the aggregate surface chemistry, the aggregate absorption, and other physical and chemical aggregate binder interface properties. All these could have an impact on the BMD test result. And such compatibility between the asphalt binder and the aggregates also needs to be considered during the BMD evaluation. Quick wrap up of the lesson that we learned out of this study. First, the interlaboratory variability needs to be better understood. As we found, our Hamburg numbers line up pretty well with the agency numbers. However, there's a significant difference between our numbers and agency numbers on the IFIT. And Aaron has just mentioned that round robin is on the table in Vermont, and we look forward to working with the agency on that. The performance test result out of production mix could be very different than the design mix. And we need to look further into this and doing further investigation to see if it is mainly because of aging or other factors. Also, binder source could have significant impact on the cracking test results, which has already been noticed by many agencies and contractors, I believe. It should also be noted that the ranking of the different asphalt binder source could also be different at different locations due to the different aggregate sources you used. Because aggregate source also matter during the BMD evaluation. Some additional thoughts say, if the mix performance is not balanced or does not meet the specification, what can we do to improve? Adjust the AC content. Seems very straightforward and always one of the first things that come into our mind. Adjust the rep percent, which is typically very effective in improving the cracking test result, although it may drive up the mix cost. Changing the virgin binder grade, especially bumping up the binder grade and making the liquid stiffer, could be very effective in improving the Hamburg or running test result. Adjust the aggregate gradation. I've heard stories from others that by switching from fine gradation to coarse gradation, their cracking test result got significantly improved. Use the help of additives such as recycling agent. Actually, there were a lot of good discussion at AAPT meetings about the use of rejuvenator or recycling agent. And with the further implementation of BMD and also better understanding of this type of product, I believe there could be opportunity between the paving industry and also the agencies to further look at this opportunity. Changing the virgin binder source, which has already been covered by my previous slide, as the binder source could have an impact. Now also changing the aggregate source seems to be challenging most of the time. However, this could still be an option at some remote locations where hauling the aggregates would be necessary anyway. And many more, I'm sure, from others' experience. Next steps for us. First of all, we're continuing benchmarking work and working with agency on the split sample testing, the round robin study, the data sharing, and also further discussion on the specification development. We will also continue our in-house evaluation on the mix out of both design and production. As I mentioned earlier, running the test isn't usually hard. However, it takes time to really understand the data and the implications behind. One of the things that we've been doing is to analyze the mixed data by correlating the different performance test results with the different mix parameters and try to identify the most significant factors affecting those performance test results. Once those factors are identified, regression models can be drawn and established in order to guide the mix design adjustment. We've also been trying to stay ahead of the curve by allocating resources on some internal studies, such as evaluating the impact of production variation on the BMD test result, selecting a proper long-term aging protocol for the cracking test, proposing different versions of performance designs according to Approach D, among many others. That's all I have. I'd like to thank you all for listening, and I look forward to further discussion with you all in a couple hours. Thank you.